Hello everyone. In this mathematics, signal processing and control engineering tutorial, we provide a clear and concise explanation of the Fourier series. In addition, we solve several examples in order to illustrate how to compute Fourier series. On top of that, we explain how to symbolically compute Fourier series in Python. The main goal of this tutorial is to provide a very concise, self-contained and clear tutorial on the Fourier series, such that students and engineers can quickly grasp the main ideas and obtain a proper understanding of the Fourier series. Also, the idea is to clarify a few misconceptions about the Fourier series and to solve several examples that can help students to better understand the mathematics behind the Fourier series. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. The main idea of the Fourier series is to represent a periodic function as an infinite or finite sum of harmonic signals. When I say harmonic signals, I mean sine and cosine functions. For example, over here you can see a rectangular periodic wave function. The function is represented by the red line. On the other hand, the blue line represents the Fourier series approximation of this function. And over here, I only take 21 terms of the Fourier series expansion to approximate this function. Note that the blue function is actually a sum of sine and cosine functions. Before we state the main formulas of the Fourier series, we need to introduce a few important concepts. First of all, consider this function. This is a periodic function. Formally speaking, the function y of t is periodic if and only if there exists a real positive number, capital T, such that this equation holds true. Capital T is called the period of the function. That is, the periodic function repeats itself after capital T seconds. Now we are ready to define two very important concepts. The fundamental period, denoted by capital T0, is the smallest positive real number, capital T, for which this equation is satisfied. The fundamental period is illustrated over here. By using the fundamental period, we define the fundamental frequency omega 0. This frequency is defined like this: 2 pi over capital T0. Now we are ready to formally define the Fourier series. The Fourier series of a periodic function y of t is defined like this. Y of t is equal to the sum, where the index of the sum k goes from minus infinity to plus infinity, and we are summing these terms. Ck, where Ck is the Fourier series coefficient multiplying this complex exponential, e to the power j, where j is the imaginary unit, multiplying k, multiplying omega 0, and multiplying time. The coefficient Ck is computed like this. Ck is 1 over T0 integral over the fundamental period interval, that is over this interval, y of t, multiplying this complex exponential, e to the power minus j, k, omega 0, t, and dt. This form of the Fourier series is called the complex form of the Fourier series. Besides this form, there are a number of equivalent mathematical forms that are derived from this form. For signal processing and control engineering, this complex form is the most useful one. In my future tutorials, I will explain other forms. At first sight, this integral might seem complex. However, it's not. To better understand this integral, let us write the first few terms. y2 of t, where 2 means that I'm only taking k is equal to minus 2 until k is equal to 2 from this sum, is equal to c minus 2 multiplying e to the power, let's see, minus j 2 omega 0 t. I just substituted k is equal to minus 2 over here. Then I have this term, c minus 1 e to the power, k is equal to minus 1, so I have minus j omega 0 t. Then I have, for k is equal to 0, c0 e to the power, let's see what do we have over here. We have j 0 omega 0 t. Then we have c1 multiplying e to the power j omega 0 t. And finally, we have the last term, c2 multiplying j 2 omega 0 t. Over here, we can observe complex exponential. However, at the beginning of this video tutorial, I said that the Fourier series is nothing less than a sum of sine and cosine function. So how can we represent complex exponentials as sine and cosine functions? Well, to do that, we need to use the Euler's formula. The Euler's formula looks like this. E to the power j theta is equal to cosinus of theta plus j sinus of theta, where theta is an angle expressed in radians. Now, by substituting every complex exponential by its Euler form, we can actually see that the Fourier series can be represented as a sum of sine and cosine functions. Next, let us explain what are the DC gain, fundamental component, and harmonics. The DC component of the function or signal y of t is the Fourier series coefficient C0. And this coefficient is computed like this. This is simply an average of the function y of t over the fundamental period t0. Then, the elements of the Fourier series expansion obtained for k is equal to 1 or k is equal to minus 1 are called the first harmonic components or simply first harmonics. That is, the following elements are the fundamental components or first harmonics. They are, let's see, C1 multiplying e to the power j omega 0 t and C minus 1 multiplying e to the power minus j omega 0 t. Then the components obtained for k is equal to plus or minus n are called the nth harmonic components or simply the nth harmonics. That is, the nth harmonics are defined like this. K is equal to either plus n or k is equal to minus n, and the nth harmonics are Cn e to the power j n omega 0 t, that's the positive nth harmonic, and the negative nth harmonic is C minus n e to the power minus j n omega 0 t. Before we proceed with examples, one very important thing about the Fourier series expansion needs to be emphasized. Namely, the coefficients ck and c minus k are related. We have that ck complex conjugate, the star over here means the complex conjugate, is equal to c minus k. Here, we will immediately give a graphical interpretation of the Fourier series. The goal is to approximate a periodic rectangular wave represented by this red line. In the sequel of this video tutorial, we will derive a formula for the Fourier series coefficients of this function. For the time being, we only graphically show the approximation for different values of k. This figure shows the approximation of the wave for k is equal to 0, and in addition k is equal to plus minus 1. That is, we only take into account the DC component and the fundamental components or the fundamental harmonics or first harmonics. The approximation is given over here. This term and this term are the first harmonics, and 0.5 is the DC component. Once we expand this expression, we will obtain this function. Next, let's see what will happen when in addition to the first harmonics, we add the second and third harmonics. That is, we compute the approximation for these values of k. And here is the mathematical form of the approximation. Over here, you can see the graphical representation of the approximation. The blue line is the Fourier series approximation. And we can see that now the approximation is a little bit better. Now, let's see what will happen when we increase the number of harmonics. Over here, we can observe the Fourier series approximation obtained for the first 10 harmonics. We can see that the approximation is much better. However, we can observe this undershoot and this overshoot. This is the so-called Gibbs phenomenon. And in my future video tutorials, I will explain this phenomenon in more details, and I will explain how to deal with this phenomenon. Now that we obtained an intuitive understanding of the Fourier series expansion, let us do a few examples. The first example is given over here. This is a periodic function consisting of cos and sine terms. The goal is to compute the Fourier series expansion of this function. For the fundamental period of t0 is equal to 0.5, this function looks like this. And here's the Python script I used to generate this graph. There are two approaches for computing the Fourier series coefficients. The first approach is to use the formula from the beginning of this video tutorial. However, as we will show in the next example, this involves significant effort. Now, let us analyze our function. Our function consists of a sum of 3 harmonic functions plus this constant over here. And consequently, we can use one trick to solve this example. Namely, from the trigonometry, we know that sine and cosine functions can be represented like this. We can use complex exponential to represent sine and cosine functions. Over here, theta is the angle expressed in radians. Now, by substituting every harmonic function in our original expression by its exponential form, we obtain, instead of 2, we can write this term. Then, by using this formula, instead of cosine of omega 0 t, we can write this. Instead of sine of 2 omega 0 t, we can write this. And instead of cosine of 2 omega 0 t plus pi over 3, we can write this. This equation can be written like this. Why did I write this equation like this? Well, while writing this equation, I keep in mind the general form of the Fourier series expansion. The Fourier series expansion involves complex exponentials that have these forms. And consequently, I just decomposed this function and I just read all the coefficients that are multiplying the corresponding exponential terms. And here's the representation. Or we can represent this function in the required Fourier series expansion form. Here it is. And from here we can see that C0 is 2, C1 is 1 over 2, C minus 1 is 1 over 2, C2 is given by this equation, and C of minus 2 is given by this equation. And that's it. Now, let us see how to use Python to verify our formulas. Here's the Python script I wrote. As you can see over here, I'm using the SymPy library. Consequently, I'm importing all the functions and packages from this library. Then, I need to define my symbolic time. Consequently, I use this function symbol, and I specify the name for time, it's simply t. And I'm specifying here that this is a real variable. Then, I define my fundamental period, t0 is equal to 0.5, and omega 0, that is my fundamental frequency. Over here, I symbolically define my function. So let's see how this works in Python. Here's why. Okay, we can see a very nice form. And note over here that I substituted the value for omega 0 and consequently obtained this expression. The main purpose of this script is to verify that these coefficients are correctly computed. Consequently, I will define the coefficient number over here. I have from minus 2 until 2. Then, in this for loop, I will actually compute these coefficients. However, I'm not going to use this trick. Instead, I will use the formula given over here. That is, I will directly use the definition of the Fourier series coefficients. And in this way, that is, by performing computations in two different manners, we will be able to verify the computed expressions. In this for loop, I'm computing this integral. I'm using the function integrate, and you can see over here what's happening. This is y over here, exponential function. Now, a few comments over here. Coef, this parameter here, is actually k. I is actually j. Note that SymPy library uses capital I to denote imaginary unit. Omega 0 is computed over here, and time is the symbolic variable. Then, over here, I specify the integration bounds and the variable for integration. The variable is t, and the integration is from 0 until t0. That is, I'm integrating this function over the fundamental period. Then, I'm using this function simplify to simplify the expression and to evaluate, that is, to numerically compute the resulting expression. And finally, I divide the result with 1 over t0 in order to compute ck. Let's see how this whole thing works in practice. Okay, now let's see our computed coefficients. Here they are. To obtain fair comparison, over here I computed C2 and C minus 2 by using the formula I previously derived. And let's compute these two expressions, and let's compare the results. Okay, so this is the C2 that I computed by using the trick, and I can see this value and I can see this value precisely over here. This means that I correctly computed C2, and here is C minus 2. Here it is. And I can see the number over here corresponding to C minus 2. And these two numbers are equal. Next, let us compute the infinite Fourier series of periodic rectangular wave. Here it is. This is precisely the way from the beginning of our video tutorial. Over here, I parameterize the amplitude. The amplitude is equal to A. The first step is to identify the fundamental period t0. From this graph, we can see that this function repeats itself every 4 seconds. Consequently, capital T0 is equal to 4. To compute the Fourier series expansion, we need to compute this integral. And let's do that. Let us solve this integral. Let us observe our function once more. This integral can be represented like this. An integral from 0 to 4, that is, over the fundamental period of the function y of t. However, what is our function y of t? From 0 to 1, this function is equal to a, and consequently over here, I write a. Then, from 1 to 4, this function is 0. Consequently, this whole term is equal to 0. And our integral only becomes this part. A is a constant and it can go out of the integration and I obtain this integral. This integral is the standard integral of the form e to the minus k multiplying some constant multiplying time. Consequently, the solution is given over here. We need to substitute the bounds from 0 to 1 and we do it over here. Next, let's do the following trick. Let us take out of this expression e to the power minus j k omega 0 over 2. As the result, in these parentheses, we are left with these two terms. Perfect. Now let's eliminate this minus sign. Consequently, I flip these two terms over here. And let's take out 2 times j from here. And let's divide this term by 2 times j to obtain this term over here. As the result, we are left with a over 2k omega 0. And here's the expression. Now, let us analyze this term. And let us go back a few steps. And we can use this formula to represent the term as a sine function. And by doing that, we have actually obtained this expression. Now, let's substitute the values for omega 0. Since omega 0 is 2 pi over the fundamental period, it's equal to pi over 2, since the fundamental period is equal to 4. Now, by substituting this term in this term, we actually obtain ck, and it looks like this. After a few algebraic manipulation, ck takes this form, and this is the final expression for the Fourier coefficient. We can also write this equation like this. What did I do over here? I simply took this term and I divided by kp over 4, and this looks like a function sinus x over x. This is the called sine c function. Okay, now let us explicitly compute c0. The issue with computing c0 is that if you substitute k is equal to 0 over here, you will obtain 0 over 0. And this is indefinite. So you need to use a trick, that is, you need to compute a limit. So you compute a limit when k goes to 0 of this term, and you will obtain a over 4. This is because the limit value when k goes to 0 of this term is actually equal to 1. This is because sinus x over x is equal to 1. Now let us verify this formula. To verify this formula, I actually wrote the Python script, and here it is. First, I import everything from SymPy library, then I define my symbolic time, I define the fundamental period, the fundamental frequency, and the amplitude is equal to 2. Consequently, I'm just substituting a is equal to 2 in order to better evaluate this formula. Okay, over here, I actually implemented this formula symbolically. And similarly to the previous case, I used the definition of the Fourier series coefficients to compute them. That is, I'm using integration method in Python to compute ck. Consequently, this expression should be equal to this expression. And let's see that. Okay, here's my c. And let's verify the integral. Here it is. That is, these two expressions are equal, and this means that I completely correctly computed the coefficient ck. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.